Okay, in this section, we're going to learn some basic counting techniques that will help us with probability problems later. So to start, let's suppose we have a game. In this game, you choose one number, either 1 or 2, and then choose one letter from A, B, or C. How many outcomes are there? Let me put it this way. How many choices are there? Probably the easiest way to show this is to take a look with your first choice is going to be a number either 1 or 2. So you could pick either the number 1, and after you choose the number 1, you pick a letter. So that letter could be one of 3 choices, A, B, or C. So this shows you 3 possible outcomes. I have 1A, 1B, or 1C. On the other hand, you could have chosen the number 2 first. And after making that choice, you still have the same 3 letters to choose from, A, B, or C. So that gives us 3 extra possibilities, 2A, 2B, 2C. So in total, we have 6 total possible choices. And you can see if you look at this table here, we have our first 2 choices, but then each choice spawns 3 extra choices. You probably learned this in elementary school, but the way to count the total number of these then is to take the 2 possible choices that you had initially times the 3 possible choices for each one once you make the initial selection. So we've got 6 possible choices, and notice that 6 equals 2 times 3. The number 2 was 2 possible numbers, and that followed by 3 possible letters. If in the previous game we have 3 numbers, so this time 1, 2, or 3, and 4 letters. A, B, C, and D. Now, how many possible outcomes are there? And from the previous example, you may have made this kind of a guess. our first choice that we choose is for a number. So for the number, we have 3 possibilities. And then we had a letter, and there was 4 possibilities, for a total of 3 times 4, which equals 12. This leads us to the fundamental counting principle. Suppose you have 2 collections of items. Let's call them collection A and collection B. Furthermore, any choice from A does not influence any choice from B, and vice versa. The number of ways of choosing items out of A is n with a little subscript a, and the number of ways of choosing items out of B is n sub B. Now, with all that, I'm finally able to tell you what this is about. The number of ways of choosing items out of A and B is n sub A times n sub B. A single 6-sided die and a single coin are tossed. How many outcomes? So for this, let's take a look at, first we will throw the die. So let's mark that. I have 6 possible outcomes with that die. On the other hand, for the coin, I only have 2 possible outcomes. So together, 6 times 2 will give me 12. The independence part of it is important. Notice that no matter what the outcome on the die is, it does not influence the flipping of a coin. nor does the flipping of a coin influence the die. So the flipping of a coin and the rolling of a die are considered independent events. Future parents plan on 4 children. How many possible outcomes are there? Here we are relying on one child being born after the other one not having anything to do with the previous child. So we are considering each child a new and independent event. So with that said, then let's mark and see how many we can have here. So let's say we have child 1, that's the first child. You can have either a male or a female. For the second child, you can also have a male or a female. Child 3, a male or a female. And child 4. That equals 2 to the 4th, which is equal to 16. In Ohio, license plates are usually of the form XXX, YYYY, where the first 3 letters are actually letters, and the last 4 are digits. So as an example, you could have the letters A, B, C, followed by 0, 1, 2, 3. So how many different license plates are like this? So all we need to do is take a look at our digits. So we'll have 3 letters. Then you've got this dash, which you can't do anything about. And then we have 4 digits. 1, 2, 3, 4. So for the letters, so this is a letter, followed by a letter, followed by a letter, and then we have a digit, followed by a digit, another digit, and a last digit. So let's see, for each letter, it doesn't say anything about us not being allowed to reuse letters or not. So I guess we can repeat letters. With that in mind, then we have 26 choices for the first letter, 26 choices for the second letter, and then 26 choices for the third letter. And then the digits, they go from 0 to 9, so we have 10 choices for each digit. And then all you do is take and multiply these all out. I know I've got a dash there, but that doesn't matter. So the total number of ways is going to be 26 times 26 times 26 times 10 times 10 times 10 times 10, which is probably easier to write it 26 to the 3rd times 10 to the 4th. And let's see what we have. 26 raised to the 3rd power don't forget to bring that down, times 10 to the 4th, and enter. So we got 17576. A lot of the problems with counting end up having huge answers, so just keep that in mind when you're doing these problems. So it looks like about 175,760,000 total. We can also modify our counting even for dependent events. So consider, suppose 10 people are vying for 3 prizes. How many possible outcomes are there? All right, so for this one, it's a little bit different. Here, we're going to match up a person with the number of prizes. But how do you choose your people and how do you choose your prizes? It's not quite as simple as what I have here because we're giving out 3 prizes. So one person can win a prize, another person wins a second prize, and another person wins a third prize. So we're actually going to have 3 winners there. So for that, let's break it down further. Let's try the following instead. Let's try first prize, then second prize, followed by third prize. Well, how many people can win these prizes? Well, you have 10 people to start with. So any of the 10 people can win the first prize. But now that somebody has won, there's only 9 people left to give the second prize to. You see, the choice, the first person being chosen, narrows the field to only 9 people. So that did affect the outcomes of what was left over. So this is a case of dependent events. In any case, once we have 2 people and 2 prizes given, we then have to choose a third person for the third prize. Well, we've already given out 2 prizes. That means 2 people have already received prizes. There's only 8 people left for the third prize. And then, as you might have guessed, you multiply the 3 numbers together for a total of 720 possible outcomes. How many ways are there to arrange 9 people in a row? So for this one, we'll take a look at the first person, the second person, third, fourth, fifth, sixth, seventh, eighth, ninth. Around out of space. So fourth, fifth, sixth, seventh, eighth, and ninth. So for the first person, we can pick any of the 9 people to occupy that spot. Now one person is put in the spot. There's only 8 left for the second spot. Now that 2 people have been chosen, that leaves 7 for the third spot, and then 6 for the fourth spot. 5, 4, 3, 2, and then by the time you get to the 9th spot, there's only 1 person left over. So this is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. In probability theory, they have a shortcut for this multiplication. You can do this all by hand if you want to, but you should be aware that we have a symbol for this. If I write a 9 followed by an exclamation point, it will equal 9 times 8 all the way down to 1. This is referred to as 9 factorial. To find it on the calculator, the Texas Instruments calculators are fairly similar in this regard. Let me turn it on. And what you typically do is you touch 9. Now on this calculator you can follow along. I hit the math button, and then see up here I'm looking for the PRB button. You can arrow to the right to get there, or another nice thing is that if you can wrap around the reverse direction if you want. But you see I want choice number 4. Once I have that, I can hit enter. And I get my 362,880. Now on the other type of calculator that is used in this class, I know a lot of those that don't have the style, look for a button on your keyboard called PRB. That's for probability. You will find it inside of there. You will find this factorial inside of there. For just plain old scientific calculators, on your keyboard somewhere is that symbol. So you have to try to find it. So as a definition, n is a whole number. Then n factorial will equal n times n minus 1 times n minus 2 times 3 times 2 times 1. And we also define 0 factorial to equal 1. How many ways can we arrange the letters in BASIC? So by that I mean rearrange the letters. How many ways, total ways, can we do that? So what we do is we look at the 5 letters that make up BASIC. And let's see how many ways we can do this. How many choices do we have for the first letter? Well, we have 5 choices for letter number 1. And then after letter 1 is set, we have 4 choices for letter 2. 3 choices for letter 3. 2 choices for letter 4. And then finally, the last letter is letter 5. So that is equal to 5 factorial. Try it on your calculator. You'll see that that is equal to 120. Now, each of the letters in BASIC was different. That was 5 different letters. What happens when you have repeated letters? How many ways are there to arrange the letters in Ohio. So we look here and we might do the same thing. We might say 4 factorial because there's 4 letters. However, that would be wrong. 24, there is unfortunately not 24 ways of arranging the letters, because if I were to instead, let's say I called this O1 HIO2, then I would have 4 distinct objects. Now I could arrange those 4 distinct objects in 24 ways. That is true. However, once I remove these little subscripts from them, you'll have half of the outcomes will be the same. So there's only actually 12 outcomes. It's close to what we have as 4 factorial, and that plays a role. We'll take 4 factorial, but then we'll notice that there are 2 letter O's. And it won't quite be that completely. It'll actually end up being 2 factorial. 4 factorial is 24, and 2 factorial is 2. So this will actually equal 12 and not 24. Suppose you have n total objects arranged into m classes where each class has identical items. So you've taken n things, broken it up into m classes. In each one of these classes, all of the items are the same. Okay? The number of ways to arrange all n items is n factorial all over r sub 1 times r sub 2 dot 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 times r sub m. And r sub 1 equals the size of class 1. R sub 2 equals the size of class 2, dot, 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 until we get to R sub m, the last class, is size of class m. The way I wrote this is so much more complicated than the way we're actually going to be using it. As an example, how many ways are there to arrange the letters in arranger? Well, the way we do this is the following. First, let's count how many items are in the whole collection. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have a total of n equals 8. So I have 8 factorial because there's a total of 8 letters. Now some of them are the same. Notice that the letter A happens twice. since I have two letter A's, I'm going to divide by 2 factorial. Now that's not the only letter that we have repeated. Notice that the letter R occurs a total of 3 times. So I'm also going to divide by 3 factorial. And you'll keep this up for however many repetitions that you have. Now none of the other letters repeat. So A and R are the only ones that repeat. The other letters N, G, and E all only occur 1 time. So I don't have to do anything with them. So let's just go ahead and get these numbers then. The 8 factorial, I'm going to need my calculator's help because I do not know that off the top of my head. So you click 8 and then Math, PRB, number 4, enter. We get 40,320. And then the denominator, 2 factorial is 2 and 3 factorial is 6. So I can simply take this 40,320 and divide it by 12. So I'll simply click divide, 1, 2, enter, and I get 3,360. Note, if you want to, on your calculator, you can also have done it this way. We could have done our 8. Let me get my Math, PRB, number 4 for factorial, like so, and then divide. Now, if I want to put the 2 factorial times 3 factorial in the denominator, I will have to encase it in parentheses. But I will not have to put a multiplication around or after the 2 and after the 3. Well, after the exclamation point, I will not have to put a multiplication. So I'll put 3. Not that that's a big deal, but let me get Math, PRB, 4, finish the parenthesis, enter, and you see we get exactly the same number as before.